The satellite cable. All right. There's a proposal to power satellite X as it orbits Earth. In this model, X is connected by an electronically conducting cable to a smaller satellite, Y. Satellite X orbits 6,600 kilometers from the center of the Earth, right? So the radius is 6600 times 10 to the third, because it's kilometers, right? There's the mass of the Earth, right? Show that the orbital speed is about 8. Well, you'll find in your data pack, you'll actually find this orbital velocity, right? Just use that. You'll get something like a little less than 8,000. Do show your sig figs, though, for that. It's less than 8,000. It's like 7,000 something. All right. Satellite Y orbits closer to the center of the Earth than satellite X. Outline Y. Outline Y. The orbital times for X and Y are different. Well, because R is different, right? So Y will actually go faster. It also, by the way, has a smaller distance to go. I didn't find that in the mark scheme, but the racetrack there is a shorter distance, right? And so the combination of going faster and having a shorter distance to go would tend to change the period, right? Okay. Why does satellite Y require a propulsion system? I thought this was more sophisticated, but, to keep it from, I guess, racing ahead or something like that. Okay. To keep them at the same spot, right? Okay. I think is what they're looking for here. Let me look at the mark scheme. Yeah. Okay. There it is. I'll let you see if you can navigate that. All right. Okay, so let's take a look at the next part here. Okay, so explain why satellite X becomes positively charged. Well, let's imagine we're looking at this from above. It's supposed to be an eyeball. Kind of looks like a TP, though, doesn't it? Okay, so let's say we're looking down at this, right? You would see a magnetic field out of the page, right? Okay. So hard to draw magnetic fields, right? And then you'd have this cable. Whoops, long cable, right? And you'd have satellite X and Y. And they'd be moving this way at some velocity. Okay, so why does X become positively charged? And the reason is that the magnetic force on this, if we use the right-hand rule, put your index finger in the direction of that velocity, your middle finger in the direction of the magnetic field, and you get that the current flows toward X. So I flows this way, okay? So why would it become positively charged? Well, in reality, it's a metal cable, right? You have to say that by the cable contains electrons, okay? And the electrons actually experience a force in the opposite direction, right? So this guy becomes negatively charged. By subtraction, this guy becomes positively charged. Okay, that's what's going on here. Satellite X must release its ions into space between the satellites. Explain why the current in the cable becomes zero unless there's a method for transferring charge from X to Y. Unless there's a method. This is kind of, I'm not sure they understand this. Okay, so let's see. It must release ions into space between the satellites. Explain why the current is less. Well, eventually what's going to happen here is that the charge is going to build up on these satellites. Okay, the charge will build up. Now, I don't know how it's going to release these ions into space, but maybe they have a way to do that. Let's not worry about that. Okay, charge is going to build up on these satellites. Basically, a bunch of electrons are going to build up on there. Eventually, the fact that there's a bunch of electrons there, as more electrons try to flow in that direction, they're repelled by these electrons, right? So there's an electric field that builds up that opposes the magnetic field, and the force becomes equal. That's what's going on, okay? And the electric field comes from the pileup of these electrons in there, or the sustained positive charge. So at some point, if you're a negative charge, remember you're going to feel a force this way, but there's also an electric force that would oppose that. Okay, that's what they're getting at here. Okay, and in the mark scheme, intriguingly, they say, well, unless there's a way to complete the circuit, right? But I'm not sure that they understand that wouldn't work. you'll see, we were going to do two problems like this. Clearly, whoever wrote the first mark scheme actually put that question on the test. But let's just consider it here. Let's imagine that we take a wire and we run that wire to here. And there's not a break in it like that. Okay? Could that wire allow these electrons to flow up there? No. No, it couldn't, because this wire would also be moving in the magnetic field that way. There also would be a magnetic force forcing electrons this way. There also would be the same exact equilibrium between the electric field and when you look at the mark scheme anyway, just maybe I read it wrong or something like that, but I'm not sure they understand that you can't connect a wire like this. Now maybe you could spray ions into space, like you could have a gas that you spray into space or something like that, and then let the positive charge jump off and go away. Maybe, I mean, that could be. And then you could have like a current flowing or something like that. But generally, unless you have like tracks. The other thing you could do is have this thing run on electric tracks. But that would be kind of expensive, wouldn't it? I don't know. All right, I'm going to stop talking here.